welcome Mr. Jeff Kowalski from Autodesk.
Thank you very much, Terry, for the kind introduction, and welcome everyone to the opening session this morning at Euromold. I wanted to give a talk today that asks a fundamental question, if I can get my slides to work. What comes after the information age? We had the agrarian age, we've had the industrial age, and now we had the information age, but my question to all of you is, what comes next? Today we've got vast kinds of capabilities. We've got great design tools, we've got infinite amounts of computing, massive data, and of course, additive manufacturing. So with all this capability that amplifies what we can do just at our fingertips, we can all sense that we're on the cusp of a new era. So what's next for design and manufacturing? Well, I think that's what I'm going to talk about today, creating tools not for the information age, but for the imagination age. The shift in trends and tools is something that we're really passionate about at Autodesk. We're a design software company, headquartered back in San Francisco, where my office is, and we make tools for people who make things. We make tools for professionals in the building, manufacturing, and entertainment industries. Our customers are the world's designers, architects, engineers, and digital artists. From skyscrapers to bridges, consumer products to cars and heavy machinery, from games to films, our customers make many of the things that we touch and see every day. 33 years ago, we released our first product, many of you probably know it, AutoCAD, which established us as a pioneer in the CAD industry. And today we offer a very wide and deep family of tools, hundreds of them, which run on desktops, mobile, and increasingly in the cloud. We create software not only for design and analysis, but also for realizing those designs. We offer a complete set of solutions that take you from ideation to fabrication. Now, a few years ago, we complemented our historic focus on the professional market, expanding in a whole new direction, making creative tools for just about everyone. Our consumer group is committed to the idea of unlocking the creativity in everyone, in any profession, any age, anywhere. Today, we have 16 million professional customers, almost 250 million consumer users, and all together, there's 680 million students with access to our software for free. At Autodesk, it's our job to give people the tools they need to help them imagine, design, and create a better world. Okay. So with that Autodesk information out of the way, let's get to the talk. Let's start our exploration about what's next with a look at additive manufacturing, not just for its own sake, but in the broader context of design and manufacturing. I want to talk about what additive manufacturing means, where it is now, and why it's so important as we enter the imagination age. Now, to paraphrase that old Hollywood saying, 3D printing and additive manufacturing have been an overnight success, 35 years in the making. Actually, the basic idea goes back even further than that, all the way back to original science fiction movies and programs like Star Trek in the 1960s, where they had that great device called a replicator. You enabled you to make anything at any time instantly with just the touch of a button. That kind of idea and that kind of machine that could make anything that you could imagine thrilled people around the world, including me. And most importantly, I think guys like these two, inventors back in the 1980s, guys like Chuck Hull and Scott Crump, who started trying to bring that inspiring vision of the replicator to life, establishing the basic concept of 3D printing. And after years of steady development, just recently, I would say around 2010 or so, we hit some kind of inflection point. And 3D printing took off just like a shot. The media fell in love with it, and all that attention fueled the democratizing maker movement, and that helped grow companies like TechShop and MakerBot. All that attention was great, And in turn, it inspired all kinds of innovation. But it also led to some heightened expectations. Now, in some ways, those expectations have been met. Today's 3D printing is a global movement embraced by millions of people around the world. I mean, look at all the different flavors of excitement around 3D printing. By almost any metric, 3D printing is spreading far beyond the realm of creative kids and inspired amateurs. The excitement in hobby-level work and rapid prototyping has reinvigorated interest in professional-level additive manufacturing, for sure. But despite the bold vision and those exciting expectations, right now 3D printing has still got a lot of problems with it. In fact, it's still kind of broken, I think. And we have to address those problems if the field is going to reach its full potential. We want it to take its rightful place alongside traditional forms of manufacturing, like subtractive or injection molding, robotic, or even biological manufacturing. Now, a way to gauge the development of 3D printing is to see where it is on the Gartner hype cycle. And if you aren't familiar with this already, the hype cycle kind of maps out how evolved the concept really is versus the hype and the conversation and excitement around it. Now, in recent years, 3D printing has reached the peak of expectations, and now we're kind of entering the trough of disillusionment, I think, which happens when the hype about something has expanded beyond its practical reality. How do I know this? Well, you can actually take a look at the stock market to help prove it out, right? We see our journey through the trough of disillusionment mapped out pretty clearly here. Does that mean that 3D printing is collapsing? I don't think so. But the big question is, how do we get out of the trough? How do we move 3D printing to the plateau of productivity? Well, first we've got to inspect seriously what's wrong with 3D printing. Now, I've been focusing on this problem, and I want to share with you some thoughts that we have from Autodesk on our point of view. We think that there's 5 things that have been holding 3D printing back. First one, quality problem. Up until now, 3D printing's been pretty good for creating prototypes and nearly good enough to become a bona fide way of creating actual production parts, but there have been problems. Problems with warping, low resolution output, and limited materials. They all keep overall quality too low. Even worse, the process has been pretty bad too. When we click print, we have very little certainty that we're going to get a successful output. You know, about 70% of prints fail. I used to joke around, that's why we've got a clear front to most 3D printers. It's so you can actually watch the print fail. We need to get to the point where 3D printing is no less reliable than 2D printing. When you print in your office copiers, you don't rush over to see if it worked, right? You just pick up the print when you're done. We got to get to that same spot with 3D printing. Third, we're using an old workflow. One based on, I would say, more traditional forms of manufacturing, and we magically think that the things that we're going to get out are going to be different just by putting additive manufacturing at the back end. Fourth, I think we're aiming at the wrong target. We think it's a success to print the same old thing that we might have injection molded or maybe cast. Instead, we should be thinking about printing entirely new things that we couldn't have made before. We need to harness all that energy that has been invested in the amateur realm of additive manufacturing and refocus on invigorating the commercial realm. And the fifth problem, and I think this is a big one, is that the 3D printing market is prematurely mature. Companies' desire for stable business models have led to bad decisions, leading the field into premature stagnation. For example, locking into DRM-controlled materials, we're limiting the potential of exploring other materials that might be better for the field in the long run. So those are the 5 things that I think are currently holding 3D printing back. And the good news is that problems like these are being addressed by thousands of companies around the world, including Autodesk. So let me show you a little bit about the things that we're doing to help address these problems. First of all, Autodesk has created a new platform that we call Spark. It unifies and rationalizes the entire 3D printing workflow, connecting it end to end so you can go smoothly and reliably from design to fabrication. Now, a key part of that is a software stack explicitly created for additive manufacturing. The stack is the foundation for applications to guarantee a one-click and it just prints workflow. Now, up until now, different software chains would give you a great variety of results. Here's something I printed on just a normal printer using the stock software that came with it. Failed. Here's one I printed with a slightly better piece of software. This succeeded to print, but the support material cannot be removed, so this print's useless. By contrast, our Print Studio tools give you this, what you expect. This is the kind of outcome that you expect. A designer's inspiration not tempered by the fabrication process. The inspiration just comes out the other end of the printer. Instead, it's the freedom to explore even the most complex designs, and you have the confidence to know that it's going to be faithfully reproduced, not jammed in the printer. This is how we're going to shift our expectations from, look, it printed, to, look what I made. I also want to let you know that last year we also introduced a reference printer, a platform that we put out called Ember. It's our first piece of hardware, and we created it simply to demonstrate what's possible using that software. Now you connect those two things together, and it demonstrates a pipeline that allows you to quickly and easily go from art to part. Autodesk is doing for additive manufacturing what Google did for the mobile world. You see, they provided Android, right? It was a platform that was reliable, consistent, and extendable, and a hardware device, the Nexus phone, to demonstrate its capabilities. And that's exactly what we're doing. Spark is the reliable platform, and Ember is the reference printer. And following that pattern, we've actually done something really remarkable. With Spark, we've made everything open. The software platform, from its APIs to its implementation, down into the firmware, they're open for contribution and collaboration out on GitHub. Even more, the hardware's open. We've published the plans for the printer Ember online, not just so that other companies can see how we did it, but so they can use our printer as inspiration for their own innovations. Maybe even more importantly, we've chosen the open materials route. We've published our formulations. We allow new formulations to be used from any supplier in our Ember printer. And we've already seen, because of this, a number of new materials, from traditional plastics to even interesting biopolymers, specifically developed for use with Ember. Taken together, Spark is a platform, an open one, for connecting software, hardware, and materials together into a manufacturing ecosystem. It breaks down barriers to entry, and it opens up new possibilities for innovation. We're also working in the community to advance a standard file format, transporting design and manufacturing data, overcoming the limitations of STL. It's called 3MF. And to help the manufacturing companies get off the ground, we've also launched a $100 million investment fund, a kind of monetary ignition or fuel for this ecosystem. And as a result, we've seen some really fascinating companies coming out. Here's one we invested in, Carbon 3D, whose super fast print technology can print in 3D in real time. Or how about these guys at Voxel 8? They're combining form and electronics into one continuous process. Look at this. Imagine printing something, and when it's finished printing, it's not just done, it actually works. Already we're seeing a wide range of companies, hardware manufacturers, software developers, materials suppliers, product designers, adopting the Spark platform. Now, we're doing all this work for a reason. In part, it's just to fulfill that bold vision of 3D printing and to make reality match those expectations. But here's the most important thing. We need this stuff to work because designing and making things is changing fast. We need to add reliable industrial additive manufacturing to our arsenal just to keep up with the set of 3 interconnected transformations I want to share with you. We call them the future of making things. First transformation, it's about how things are designed and made. That's production. The second is about what customers care about and want, which is demand. And the third is about the nature of the products we make. Let's talk about those. The means of physical production is changing. We can't design or build things the way that we used to. Complex production methods are required to bring products to market faster. Supply chains are being disrupted, and things like microfactories and a decreasing reliance on big companies is changing the landscape. Now startups and entrepreneurs compete with established players. Using those new means of production, we see people creating even traditional things, big things like buildings, with some very non-traditional processes, forms, and materials. So take this example. It's back from San Francisco. This is the new facade on the Museum of Modern Art. There are 700 facade panels on that building. No 2 are the same. In order to make that, they had to apply very novel manufacturing techniques. And because we're in an earthquake zone, it can't be too heavy. So they couldn't make it out of concrete. They made it instead out of fiber-reinforced plastic, and they shaved off, they removed 500,000 kilos from that facade. Next up, there's demand. A new, more savvy customer class is emerging. Today's customer cares about how things are made, what that product is made of, and where it is made. And their relationship with products and producers are becoming much more complex. In fact, even more than how something was made, the customer cares about how it was made for them. This means companies need to get a lot more agile and adaptable and make things specifically for individual customers. For example, I know it's a trivial example, but today, you can walk into a store, scan your ears, and walk out with a customized set of earbuds made just for you. Or you could do the same thing, scanning your ears with your iPhone at home and have them shipped to you. Customers want personalized experiences and customized products, and they're going to buy from companies that can provide both. Finally, third is the nature of the things that we make. It's also changing fast. Today's products are deeply interconnected to each other and to other systems, both physically and digitally. For years, things had coexisted independently, but that's changing. Products are now part of interconnected digital systems. Even things like factories and design are connected together. Now, for most of the years since the dawn of the Industrial Revolution, we've been really concerned about making just the thing. But today, there is so much more to and so much more in the things that we produce that it can't be captured and delivered using the mindset that we had created for ourselves during the industrial era. Manufacturing is now not just what we make, it's what we make happen. The very idea of what a product is, who defines it, all of that is changing. And that means that the tools and processes we use to create products also has to change. So given this new landscape, what kind of tools do we need? What are the characteristics? I'll tell you. The new baseline for us to succeed in the world boils down to 3 things. First, I strongly believe that the tools have to live in the cloud, because that's the only way companies are going to get the scalability that they need in terms of computing power and tools. In the cloud, the tools are never obsolete, constantly updated to meet shifting needs. Second, these new tools have to be centered around collaboration, bringing together people from different locations, different companies, different disciplines. They'll put the collaborative process at the center of the experience, with tools and data augmenting and enriching that process. And thirdly, the new tools will unify a complete workflow for users, bringing together modeling, rendering, animation, analysis, and fabrication, and giving them the sensation and experience of one process, rather than a bunch of disconnected, often warring functions distributed across different packages with file interchange formats. Now, these new realities demand new kinds of tools. And to address these challenges, we've assembled the capabilities into a solution we call Fusion. Fusion is a cloud-based platform for industrial design, manufacturing, engineering. Fusion is more responsive to those changes I was mentioning about the means of production, consumer demand, and the nature of products than any single desktop solution could possibly be. Now, we built it in the cloud, so it runs in your browser, and it's designed to specifically address the challenges of this new world. It's always up to date, it has design and collaboration built right in, and it brings design, simulation, all the way out to fabrication, all together in one package. Just a minute, yeah. And to bring that full circle, Fusion connects to Spark. Here we see a Fusion model that's being brought into the Print Studio service within Spark. And I'm going to put it on the build bed. I'm going to find out that it's too big, so I'm going to cut it. It's automatically going to dowel it for me. I can preview that doweling, see how it fits in. Next up, it's automatically going to generate optimized support material. And finally, I can preview the build. Now, the beauty of this is that we finally have a tool to exploit the capabilities of additive manufacturing, particularly its flexibility and agility. Okay, so we're providing Spark to help fix 3D printing, and we created Fusion that connects design directly to manufacturing. Sounds like we're done, right? We're all set for the future of making things. Is that really good enough, though? I don't think so. I think the answer is no, because the industry as a whole is still being hampered by outdated mindsets about design and computing very fundamentally. Now, I want to take a look at how those mindsets are hampering us. And let's do so by looking back to the beginning, the very, very beginning of CAD. Here we see Ivan Sutherland. At MIT in 1963, he was the inventor of the very first CAD program, which he developed. It's called Sketchpad. Now, it's amazing to me how little CAD has really changed since the days of Ivan. The most shocking thing is that 52 years later, we still recognize that as a CAD program. Now, despite our long history of innovation at some basic fundamental level, we're still right back where we started. Of course, there's been tremendous progress in the world of CAD since Ivan's day. But in many ways, I gotta tell you, the computer still hasn't really aided us as we did our designs. In fact, if we're really honest about it, CAD has never stood for computer-aided design. In all of these years, I think it stood for computer-aided documentation. We did the design in our own heads, and we only used the computer to document what we thought of. Similarly, in the world of CAM, and I know I'm going to get in trouble for this at Euromold, I don't think we have computer-aided manufacturing yet. I think we have something closer to computer-automated milling, molding, and machining. So what's been standing in the way of real CAD and real CAM all these years? I can sum that up in one visual. The classic C prompt. You remember this? It symbolizes the way we've always used computing. Traditionally, we've used computers as passive tools for execution, just sitting there with that prompt, waiting for us to tell them what to do. So how can we use the computer for something more? How do we make it a real partner in exploration? The answers to that question are an exciting new set of capabilities that computers have very recently just begun to develop and effectively demonstrate. Now think back to Ivan at MIT and that first CAD system. Back then, there were two things, two essential resources that were extremely scarce and inflexible: computing and manufacturing. The very structure of our CAD and CAM systems is predicated on the scarcity of those two resources. But here's the thing, those days are totally over, right? Today, computing and manufacturing power has been radically democratized, which means that the two things have gone from scarce to tremendously abundant. Infinite computing, we've already got it. This is about computing so cheap and available, it would have been unthinkable in Ivan's day. Infinite computing is such a powerful force. Mark Andreessen used it in part of his description, software is eating the world. You heard that? It's powered by infinite computing. And in the recent years, this force has been completely digesting and reconstituting product after product, market after market, and service after service. Now we got to get ready, because those sorts of disruptions, Spotify, Airbnb, Uber, those radical disruptions are coming to our world, turning limited computing into infinite computing, scarce manufacturing into flexible, expressive manufacturing, the kind we're going to get by fulfilling the promise of 3D printing. And when we combine infinite computing with flexible, expressive manufacturing, we get infinite expressibility, which means that today we're getting very close to being able to design and imagine anything and create it. This force is coming at us like a big force of nature, right? And I want to contemplate for a moment what the distinction is going to be between those who get flattened by that force and those who are able to ride the wave to greater success. I think that companies that are used to competing on their sheer ability to execute through access to computing and to manufacturing power are going to find it increasingly difficult to stay afloat. And I think those who are going to ride the crest of this wave are going to be the ones that take the abundance of computing and manufacturing for granted and instead focus on the two new determinants of success: their imagination and innovation. Those are the business critical ingredients now. I'm talking first about pure imagination, making up things that are new and different, and then innovation, bringing those new things out into the world. All right, so let's think about this for a second. If it's true that imagination and innovation are the new essential elements of success, what kinds of questions should you be asking yourself to prepare for this competitive reality? How does such an impending sea change, so to speak, affect your strategic planning? Now, I'd argue that one of the most important questions to ask yourself in the face of this new world is actually a pretty simple one. Who do you want to work with? In a world of infinite expressibility, what kind of characteristics would you be looking for in a colleague, in a designer, in an engineer? I know how I'd answer that question. I'd want someone who would bring a wealth of experience to the job, who'd be curious enough to explore more alternative solutions than I would ask for, someone who'd use spare time to play with more ideas, and someone who would continue to learn and reflect as we worked on projects together. Those are the characteristics we expect from the people we work with, the people we hire, right? Shouldn't we also expect them from the computers and the software we work with? Why the double standard? For example, if you hired a person and they got no smarter and no more experienced a year into the job, what would you do? You'd fire them. And yet with computers, we're unbelievably patient. We use them the same way every single day, and they never get smarter, and somehow we're fine with that. Now that's got to change. Today, we do not have to be satisfied any longer telling the computer just what to do. Instead, We should tell the computer what we want to achieve. This makes the computer not a tool just for execution, but a partner for exploration. And this new capability, I think, is really going to fulfill the acronym CAD, Computer as Designer. And the reason that we can finally think of computers as our partners stems for two essential capabilities that we're now introducing: creativity and learning. Let's start talking about how computers are being more creative. This is something you could also call right brain computing. You know, for 30 years, we've been working on that left brain, that left side, the analytic side. And now we're going to work on the other side, the creative side. This means that computers actually need to come up with ideas on their own. And this is the heart of something that we call generative design. In generative design, we share our goal with the computer. We tell it what we want to achieve and the constraints that are involved in that challenge. And then it's the computer that actually explores the solution space to find and create ideas that we wouldn't have thought of. Now, let me give you an example to help you understand generative design a little bit. Here's an antenna that was designed by hand at NASA in the 1960s. It went out on space missions. And it was designed by a professional electrical engineer, and it was thought to be a very, very elegant, high-performance design. That was in the 60s. But about a decade ago, a groundbreaking development changed the design of those NASA antennas forever. Engineers developed an algorithm that created and analyzed thousands of possible antenna designs automatically, simulating their performance and progressively evolving higher performing solutions. Now, this design over here, although it looks kind of strange, performs twice as well as the one that the human expert created. This is an early example of generative design, but it still helps us illustrate what generative design can do for us. Generative design moves us beyond our own best efforts to best outcomes. Let's take a look at a mechanical example. Why are bicycle frames triangular? We've built bicycles the same way for years and years. And I don't know if we've ever asked ourselves that question. Up until now, we haven't had the tools to evaluate all the options, and we haven't had the means to manufacture other shapes. But now we do. Let's take a look at some of the tools that transcend those limitations and help us get to some of these provocative designs. One of them is a product called Within. It's specifically designed to optimize for performance, weight, and manufacturability simultaneously. It uses an approach called multi-objective optimization, and you can ask the computer not about trade-offs, meaning can it be light or strong, but instead give it both parameters and ask it to solve for them together. Lattice hollow, lightweight parts that are just as strong as those that might have been cast or milled solid, they're revolutionizing industries like automotive and aerospace. Now, historically, we've seen a big difference between the things that have been designed by nature and the things that have been designed by us. Now, there are opportunities for us to take more direction from nature, I think, in the strategies that we use. Take bone, for example. If our bones were solid, they'd be much, much heavier. And we'd be much less efficient, and we'd require a lot more energy just to survive. It's the interior lattice of varying density and thickness that keeps bones strong and light. There's more bone where it's needed and less where it's not. In nature, form follows forces. We can achieve the same simultaneous optimization of strength and weight in software. Now, this is obviously beneficial in healthcare. We used to see medical devices and appliances that were bulky and generic and uncomfortable, but today we can create custom devices, making them elegant and biomorphic, and make them light and strong. In fact, as we see with this facial implant, we can imbue them with even sophisticated functionalities like specifically designed porous structure that integrates with the bone of the patient. It's a whole new level of performance for a product like this. And this part of optimization can have a dramatic effect even in other trades. And since we're here at Euromold, why don't we take an injection molding example? Let's think about some of the plastic parts molded for this food processor. Now, here's a scene from MoldFlow that shows the in-mold temperature of one of those parts. It's super hot. It's going to take forever to cool, and it's going to warp. So we can add conformal cooling to radically change that temperature profile, right? And now it's only going to take about 5 seconds to cool, part quality is preserved, beautiful, right? How the heck are we going to make it? Here's the core cavity that produces that optimal cooling. How do we manufacture something like that with embedded cooling lines? Straight through drilling is not going to work. Well, here's how we do it. Start by looking at the pressure inside that cavity. Here we can see the areas of the mold that are critical and those that are not. And then we get the design automatically optimized for strength and material using within. The lattice thickens where needed, and the cooling lines are automatically integrated. Nobody drew those lattice struts. The software sized them to resist the pressure in the mold automatically. And you could print this now with substantially less material than a solid block, right? Perhaps you'd print this in a strong steel, it would come out quicker because there's less material, and then you could fill it with a thermally conductive material like iron. All right, now I want to explain a little bit more about generative design, this time looking at a motorcycle swing arm. Now, this is a structural part that holds the back wheel to the engine mount of the shock, to the shock mount. A famous biologist in 1915 said, "The form of an object is a diagram of its forces." I think that's actually kind of beautiful. And we've actually adopted that concept quite literally, translating it into the CAD world. We have a research project that we call Dreamcatcher that lets designers describe the forces that act on an object, and then the computer will make it. Now, these forces can be structural loads like we see here, or they could be manufacturing methods. I want to make it this way, or I want to make it this way. Or they could even be stylistic preferences. Oops, so sorry. Now, traditionally, when a designer wants to narrow down some options, they start in the solution space of their recollections, right? Things that they might have designed before. But truthfully, these spaces that we have to search through are getting enormously large these days. What happens if you want to swap out a material? What happens if performance requirements change? Design permutations and trade-offs can boggle even the most experienced design minds. Traditional CAD tools, I think, are completely played out for this type of example, even when they're paired with design geniuses. They're going to fail to solve the complex problems of the future. So instead, let's take a system like this, a system that we're calling Dreamcatcher, that solves the problem directly. Given the forces, it creates form right where needed. In this video, you see material that's being moved to just where it's needed. It's both being eroded and added. Think about doing this for all types of ranges of materials. You can do it for aluminum or titanium or whatever. I actually brought a printed version of that exact part for you guys to manipulate after the talk. This is a version of a part for that swing arm if it were printed in titanium. It'd be too expensive for me to bring all the way to Europe. So I printed it in nylon instead. But it's the same form. And one of the things that's so amazing to me about it is, check this out. It's actually asymmetric. Look, this side's solid. This side's got a hole. Why is there a hole on one side? The chain's on one side. The chain's on one side and makes an asymmetric load. But if you go outside and look at motorcycle swing arms that are out in the parking lot, you'll see most of them are symmetric. What I think is so interesting about this is, even if you do not choose to manufacture this design, the software is able to give you an insight into your problem. Okay, I'm going to take a deeper example on Dreamcatcher to show you the workflow. Let's say that I want to design the roll hoop for a Formula One race car. It's that part right behind a driver's head. Now, the old way to do it would be to start with an idea in your head and then design it in the computer, and then you test it to see how it works with analysis software, and you do this exactly one time. With Dreamcatcher, you start an entirely different way. You share the goal with the computer, telling it not what you want to do, but what you're trying to achieve. You describe your problem as a problem well stated to the computer. That's the inspiration phase. And then using generative methods, it's the computer that actually creates the large set of potential solutions, automatically synthesizing them using cloud computing to address that problem. But here's the key. In the time it would have taken you to do just one design, Dreamcatcher has done every one of them. And then the design proposals are made back to you in an Explore tool, so you feel like you're kind of steering through the solution space, and you get to understand the trade-offs between various solutions. Now, you might find something interesting that helps you redefine the problem again, and you can repeat the loop. But ultimately, you're going to select one to fabricate. Now let's take a look at this in action. We've actually taught the computer using natural language processing, believe it or not, to read the spec of the Formula One sheet. So it downloads that from Google. It's going to look in there and find the specifications. Next, you're going to see it translated into an intermediate format that it uses internally called sysml. It keeps the requirements in mind. Now, this is all happening automatically by the computer. So far, we're still sharing, I want to make a roll hoop to the computer. Now, once it's set up all of those things, it goes off and it generates all the designs and brings us back to the next step, which is this, the Design Explorer. Every one of those dots that you see in the diagram is a well-optimized solution to the problem. And what I'm doing here is picking in between them and looking at the trade-off between the part and cost. In a minute, I'm going to change from material to another type of trade-off. I can explore this highly multidimensional space of solutions that the computer has provided for me. Here's a couple that I'm saving to investigate for later, for deeper inspection. You notice I never drew anything. Okay, so I found clusters and interesting combinations, and ultimately, I decide I want to print it. So here's a roll hoop that was designed by the computer from requirements document with no human drawing. And just as you've done with that kind of outer topology, you could take some of the inner latticing work that I was talking about, that bone structure, and you could bring that inside to engineer at the macro levels. You can create new types of functionalities inside of objects, changing their behavior, in fact. I like this example. This lattice structure here, when you compress it, actually increases lateral stability due to the locks that it has. And you could bring all that stuff down to multiple scales. We don't have to design big things. We could design things at the micro scale, too. We're working together with Lawrence Livermore Laboratory to create architected materials that behave differently in the Ashby chart. So, for example, when you heat up these particular kinds of metals, they contract, they don't expand. Or when you stretch them, they actually shrink. Up until now, when we've talked about multi-material printing, what we really meant is simply color and aesthetics. But now I think we're going to enter an era with architected materials that's going to help us get to functional gradients. Imagine using a system that takes your requirements and actually creates a material on demand to satisfy function. This is why at Autodesk, we are exploiting this intersection of generative design, advanced manufacturing, and architected materials. And the main point I want to make here is that all of these kinds of creative computing systems are going to give us more flexible additive manufacturing. That's what RealCAM and RealCAD can achieve. So what we just saw was the computer becoming creative, generating ideas for us and with us, helping us develop them. Now I want to talk just a minute about another ability that has been traditionally reserved for humans, and that's the ability to learn. As computers are getting better at being aware of what's happening around them, they won't start dumb and stay dumb. They're going to get smarter and smarter over time. And here's a simple parallel from everyday life. Here's my puppy. My puppy is smarter than my design tools. It learns that when I pick up the leash, it's time to go out for the walk. How did it learn that? Because I pick up the leash and we go out for a walk, and that happens so many times, it finally just got that through a Pavlovian process, stimulus and response. If a dog can do it, how come our software design tools can't do it? Well, interestingly, they increasingly can. I want to share with you this example, which I think is one of the coolest things I have ever seen. These labels on these photographs were generated automatically by a computer. The computer was shown millions and millions of images as a training set, and now it actually knows how to label things that it has never seen before. These are actually pretty complicated pictures. They're noisy, right? Look at this. A group of young people playing a game of frisbee. That white thing is the frisbee, but it's only a little line. How the heck did it know? You know, we're going to take that exact same thing and we're going to apply it to design software. We're going to bring it to analysis. You know, the funny thing about all the analyses that we all run a lot of analyses, right? What happens when we're done with the analysis? We throw it away. The computer has amnesia about it. And every time we want to run another analysis, like computational fluid dynamics, which is very costly, very compute intensive, it starts from scratch again. But what if instead we put a machine learning system in the loop? So every time we analyze something for its aerodynamics, we got an impression of the connection between cause and effect. And we did that over and over again. Well, you know what? Eventually, we're not going to need the CFD analysis tool, because we're going to have a machine learning system in there that has a hunch, it has an idea, it has a gist of what aerodynamics means. And then I would be able to show it a brand new thing it never saw before, and it could tell me, give me an opinion about whether or not it was aerodynamic. Of course, it could always go in and really do the analysis when I really wanted it to. But the important thing is computers are very quickly going to start having opinions. I think that's pretty remarkable. I think it's interesting, too, to imagine what if the computer were actually doing this in its off hours? What if it were generating new forms on its own, putting them through analysis, and seeing the relationship of cause and effect? Those kinds of systems that understand those linkages start getting hunches about things and the things that we're working on. That's the kind of taught machine I want to be working with. And I think that that taught machine starts changing the partnership that we have with design tools. We get a computer aiding designer, one that rises to help us meet our goals. That's the kind of computer I want to hire. Now, how many times have we talked about learning a design tool? I think it's about time we had a design tool that learned us. Computers and software are no longer just libraries stuffed with passive data and static code. Today, they use lessons from their interactions with us, and they move down this continuum, maybe even joining us someday at wisdom. Creativity from the computer and its ability to learn, it changes our relationship with our tools. In the past, we had a solely directive relationship with computers. We tell them what to do and they would do it. Today, we have generative tools where we tell the computer what it is that we want to achieve, and it gives us a wider range of outcomes. Next, and ultimately where we're going, is a higher level of partnership for computers. We should expect them to come to work with context, pattern recognition skills, and the ability to learn from their interactions with us. We can think of them as curious and experienced, just like a valued human professional. In fact, if experienced computing is a combination of creativity and learning, we could even use the term experienced systems to describe these next computers. We're literally coming to the point where computers can understand problems with us, explore our goals together based on common experience. Then the computer can explore solutions and eventually even manufacture directly into our world. An experienced system like this meets us at our goal and serves as a true partner to us. Experienced systems, new breed of digital tools that create and learn. They've given us an incredible power of infinite expressibility to create whatever we can imagine. We're moving well past, can it be done? And instead, we focus on what could we create and why. This is a world reliant more so than ever before on imagination and innovation. Those are the twin engines in a world of infinite expressibility. And the great news about imagination and innovation is there's something we're all empowered with. For all of us in this room, we've had it all along. Imagination and innovation are the things that made us so passionate about designing and creating things in the first place. And despite the tools that have limited up until now, we've got a new set of tools just ahead that are going to bring us to our full potential. At Autodesk, I am extremely excited to be working on tools for the imagination age. Thank you very much.